We're going to take a look at this. We're going to use these three data values as our averages. So we're going to look at the mathematics behind these three. All right, so 2.38, 0.73, and 0.54. The first two are both in meters there, so we know. So let's take a look at the math that's involved. So first we'll look at projectile motion. Then we'll see what we get for a spring constant using energy methods. So to begin, what we want to do is to look at the x and the y directions like we've done in the past, where we determine some sort of a value using projectile motion. So in the x direction, jot down the x that you got as the average range. Jot down the x value that you got there. And I'm using 2.38 meters as my value. This again was the average of the groups. Then I'm using the time that was the average of 0.54. Whatever the time you had was, jot that down right there. 0.54. Now, that's not the same time as the time in the y direction. Look at the y direction and read what I put in parentheses. On the way down. Now you got to think back. Think back to when we did projectile motion problems. We talked about the problem as really having two halves of it. First half of the problem is the projectile on the way up. It gets to max height. It pauses vertically instantaneously, and then it starts to come back down on the way down. So we're going to have to look at the y direction a little bit differently. So let's first start with the x direction. In the x direction, if we recall, we know that there's no acceleration, because gravity, the thing that accelerates an object, only works vertically. Gravity pulls down, as we recall. So there's no horizontal acceleration as always. Ax always becomes 0. And we've always said this year that we're going to use only one equation in the x direction at all times. And this is the equation right here. Vx is equal to x over t. Now, when we have an angle that we're given, we're able to determine that angle and use it with cosine and sine. But we don't have to worry about that right now because we know what the actual x displacement is, and we know what the time is. So let's take our displacement of 2.38 meters, the x displacement, and divide it by the time period of 0.54 seconds. This will give me the velocity in the x direction, which I know is the same throughout the whole problem because there's no acceleration here. So for my number, I'm getting around 4.4 meters per second. Again, if you're using your own data right now, you're going to get a number that's a little bit different. That's fine. Okay, so if you want to challenge yourself, again, use your group's data and go along with it. Simple calculation, right? Divide x by t. Now, again, we need to make sure this is very clear. The value of Vx is a constant in all of these problems. Remember, gravity only affects the y velocity. Gravity makes the velocity increase on its way down to the ground, negatively. Whereas in the x direction, remember when an object is launched, okay, it's traveling with the same x velocity the entire time. It's what's happening is this. It's slowing down in the y direction, slowing down in the y direction. It pauses in the y direction, but it's still moving left, or in your case, right. And then it starts to move negatively and to the right. So the y velocity becomes negative now, but the x velocity is still 4.4 meters per second. The other reason I remember that this is never going to change is because acceleration is 0. Whenever acceleration is 0, your velocity must be constant. Definitely something for the midterm that you need to understand and know. Most of you remember that already, but whenever you have acceleration equal to 0, you got to be moving either with a constant velocity or really no velocity. But even if you have no velocity, it's still constant. It's constantly 0 in that case. Okay, so in this problem, the velocity in the x direction is 4.4 throughout the entire problem. When the catapult is launched all the way until it just hits the ground, the x velocity is always going to be 4.4. Now, the y direction is a whole other case or story. If you recall, the object is launched from here. It gets to max height, and then it continues its path on the way down and it hits the ground over here. On the way up, the velocity starts and then it decreases, it decreases, it decreases, until Vy becomes 0 at the top. Okay, Vy in the beginning has some velocity, it's some number. We don't know what it is, but there is some initial velocity, okay, here that is launched with. And then at the end, there's some Vfy. Okay, there's some Vfy at the end of this problem. But what we're looking at in the y direction is the velocity on the way down. So starting at the top of the parabola, falling down to the ground. If we're starting at the top, the velocity in the y direction at the top, again, is 0. So we can start by making that 0, which is already done for us right here. But what's the time going to be from the top to when it impacts the ground? Not the whole trip, but from the top to when it impacts the ground. What's the time in this case, Kat? It is half. Very good. So whatever your time was in the x direction, just halve it. For me, half of 54 is 27, so I'm going to put 0.27. Depending on your time in the x direction, just take half of whatever it was. Why is this true again? We assume the parabola is, what's the word? Symmetric. Okay? We assume it is symmetric. It's not always true, to be honest. Okay? On the way up and the way down, air resistance impacts a motion of a projectile differently, but we're assuming that there's no air resistance anyway, so we can say that these are symmetric. Now, it takes that much time for the object to hit the ground from the top of its path. We know the velocity at the top of the path is 0, because it does pause up there at the top for an instant. And then it starts to become negative, 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 negative velocity until it hits the bottom. Our goal is to find out the velocity on impact. Okay, Vfy. We know Viy is 0, so this bottom part here becomes 0 plus a times t. Okay, again, if you want to find out the final velocity, Vfy equals Viy plus at. Since Viy is 0, we don't have to worry about that portion of the formula. It goes to 0. So we get really negative 9.81 times 0.27, or whatever time you had for your groups. Giving me around, I'm going to give you one more decimal spot this time. Well, I'll actually round it. 2.6. We'll leave it at that. Negative, obviously, because it's a velocity going down. Now, again, your answer might be a little different from your group's data. The process is what's important right now. We'll get different numbers, and we'll talk about those numbers and how they're different or why they're different. So we've got the x velocity, and we've got the y velocity. But the y velocity is the velocity at impact, when it's about to strike the ground. Therefore, we could look at this next statement here and say the following. Since the horizontal velocity is constant and we have the final velocity in the y direction, we can say that we have the final overall velocity. And the way we do that is by using Pythagorean theorem. Think back. Pythagorean theorem tells us that a squared plus b squared is equal to c squared. Well, this is the velocity right here. In the x direction is to the right. The velocity in the y direction is acting down. So therefore, the overall velocity looks like this, which makes sense. Think about the parabola. When it impacts the ground, the velocity or the object is moving down and to the right. So that's why this VF is drawn down and to the right. Okay, again, it's moving this way in the x at the end. At the very end, it's moving this way in the x, and it's moving this way in the y, therefore giving you some sort of a downward right angle or trajectory of VF. So in order to find that, think about Vx as A, think about Vfy as B, and think about Vf as C. A, B, C of your triangle. Therefore, Vx squared plus Vfy squared equals the final velocity squared. So let's come up with a number for this when we solve for Vf. So you're going to square both of your velocities from the last part. Add them together and take the overall square root of that. So we've got the square root of 4.4 squared plus negative 2.6 squared. And remember, the negative 2.6 squared has got to be positive because you're squaring it. So you don't even really need the negative there. I'm getting 5.1 for mine. And think logically for a second. Go back. This is where you have to recall prior knowledge. If the overall velocity of impact is 5.11, then Vx and Vy have to be smaller than that. Remember, whenever you found Vx and Vy in our class, we did Vx was V cosine theta, Vy was V sine theta. It was always smaller than the actual velocity. So if we started a problem where the actual velocity was 10, we found out Vx and Vy, they couldn't ever be bigger than 10. They were always smaller than 10. Well, now look at what we've got. 5.1 is the overall velocity. And look at the two velocities we had in the components, 4.4 and 2.6, both of which are smaller than 5.1. Just to make a quick sanity check. So that tells us that the velocity of the wooden projectile on impact, when it hit the ground the first time, right, on impact, is 5.1 meters per second. What kind of energy does the projectile have the instant before it hits the ground? So it's launched, it's about to hit the ground. What kind of energy does it have the instant before it hits the ground? I definitely agree with kinetic. I don't agree with potential. Why wouldn't I agree with potential? Can somebody explain that part? It's definitely kinetic. You're right about that.
I thought because it's going down, it's like past the max height.
Not because it's past the max height. That's why I agree with kinetic. But I said, why is it not potential? It could have potential while it's moving. Remember, at the top, it's moving with potential. Why doesn't it have potential? Where is it physically located?
So the instance before this ground is basically at ground level.
Yeah, it's basically at ground level. Look at the parabola right here. It starts at ground level. It reaches max height. Then it gets back down to ground level. So the instant before it hits the ground, you could say that there's no potential energy there because its height is insignificant or it's negligible. It's just pretty much zero. So if we look at the next diagram down below, okay, take a look at the next diagram here. We're going to see how I identified all the types of energy for you. So, when you started this problem, the object or the catapult was pulled back, right? You pulled back on the catapult. Before you let go of the catapult, it had energy stored in the spring. It was a torsional spring. We'll talk about what that means in a little bit. But there was energy stored in the spring. It wasn't moving before you let go of it. It had no height. You pulled it all the way back before you let go of it. So it only had spring energy in the beginning. There was no regular potential and there was no kinetic in the beginning. Then it's launched. Along the way up, it loses energy due to air resistance. Q loss. It gets to the top. At the top now it has height and it's still moving at the top. Remember, when it's at the top, it's moving horizontally still. It pauses vertically so that it could go to the top and come back down. It's got to pause vertically. But horizontally, it is most definitely still moving. So at the top, because it has height and it's still moving, it's got both potential and kinetic energy at the top. It loses energy again on the way down. And then at the very end, right before it impacts the ground, it's got no height anymore, so there's no potential. It's not a spring anymore, so there's no potential spring. But it still is moving that instant before it hits the ground with this much velocity. So it has kinetic energy at the end. So what we're going to do is we're going to analyze these different instances of energy in order to eventually determine some characteristic of the spring. So we're going to work our way backwards. So we solved for final velocity a minute ago. So using that final velocity and the mass I gave you right here, here's the mass of the wooden projectile, 1.5 grams. Using this mass and this velocity, come up with the kinetic energy at the very end. At the very end. What's the formula for kinetic energy? Recall, what is the formula for kinetic energy? Kev?
Is it 1/2 mv²
It is. And since I'm looking for final, I'll put VF, just to specify. So I remember that I need to convert my mass, because it's in grams. I need to convert that by moving the decimal 3 spots. It's going to be a very small number. It's going to be a very small number, and you could probably figure out why that is. Why is it going to be a very small number? Why will it be a very small number looking at this? Use common sense. Why is our answer going to be small? Kat? Yeah, the mass of this thing is so small. And kinetic energy is a function of mass and velocity. Velocity is a relatively, not large number, but large enough. But the mass is quite small. So we have 1/2 times our mass of 0.0015. That's the mass of the projectile. It's the same for everybody. Now your velocity might differ. I got a number of 0.0195 joules. And keep 4 decimal spots here because these numbers are going to be very tiny here. I got 0.0195 joules as my amount of energy at the end of the problem. Again, if you're using your data, it might be a little different, but it should still be a rather small value. Okay, assuming, how many people are using their own data right now? Just give a heads up. What did you guys get? Just tell me real quick. What did you get for your VF in the previous part? I got 5.1. What did your group get?
6.37.
Okay, so yours is going to be a little bit bigger than this. Yours is going to be bigger than this also, a good amount bigger. 3.2 meters per second. So yours should be smaller than this number. Okay? Now, that tells us the amount of energy that this projectile has as it's about to hit the ground. As it's about to hit the ground. Now, consider and think for a second. Use conceptual understanding here. At the top, is it going to have more or less energy than the amount of energy it has at the end of the problem? Again, at the top of the path, is there going to be more or less energy than what you see right here at the end when it hits the ground? Give me reasoning too. Don't just give me an answer, but reasoning behind.
At the top, I guess it would have
Velocity is not zero at the top. Read, look. We have potential and kinetic energy at the top. So it can't have 0 joules. If it had 0 joules, the conservation of energy wouldn't hold true. Right? Kat? Stick with the first part you described.
Q loss.
Yeah, what is Q loss doing?
It's like decreasing the energy.
Exactly right. On the way down, the projectile loses energy because of the friction in the air. So at the top of the path, it's got to have more energy than it ends up with at the end because it lost energy on the way down. That's what Q loss means. So if we want to figure out the energy at the top, which we're going to do, PE plus KE, we'll do that in a minute, the answer we get should be bigger than the answer we just got for part 1 here. So let's go to the next page now to figure out PE plus KE. Now, how can I find PE? PE is mgy. That's where your Y max is going to come into play. So if I want PE plus KE, I'm doing this. mg times Y, which is really Y max, plus 1/2 m. Now, the kinetic energy at the top, if you recall, is from Vx only, because Vy at the top is 0. So this is really 1/2 m Vx squared. All right, so again, the PE from the top, you have to use mgy max. The KE at the top, you have to use 1/2 m, and we're using Vx squared, because Vy is 0 at the top, so we don't have to use that part. So when you plug in your numbers, go back to your first page to figure out these numbers, or your second page where you listed these values. Remember that with energy, 9.81 is positive. Please remember that. Only with projectile motion do we call it negative there. So again, your Y max might be different. I'll underline that in blue. Your work might be different right here. .73 is your Y max. If you go back up, look at your data. Your average Y max. Go back up to your data, all the way back up. Yeah, see the Y max you had? Okay. So again, the two things that are underlined in blue might be different for your group if you're using your own data, but everything else, the mass and gravity, and that all remains the same. So I'm going to go ahead and calculate what this number gets out to be. I got a value here of 0.0253. When you finish part 2, please read part 3. Try to make sense of what number 3 is asking you to do. It's saying compare the last two answers you got. If you have the energy at the top and the energy at the end of the problem, you subtract the two, you should get Q loss. So number 3 is telling you figure out what Q loss is by looking at the difference between your answers from numbers 1 and 2. If you look at that equation here, that's what this states. If you just subtract KEF, you get Q loss, right? So subtract KEF from the energy at the top. And if it helps you to do this, this is what I would be doing maybe in my notes. I would say this is the top, right? This is the end of the problem. So if you take the energy at the top minus the energy at the end of the problem, this is where you get Q loss from. The top energy minus the energy at the very end will give you Q loss. So take the sum of PE plus KE from number 2, and subtract KEF from number 1 on the previous page to give you Q loss.
I don't know why, but that's something.
Let me take a look.